Let's continue our discussion on partial differential equation with solving hyperbolic equation by using finite difference method. And our focus for this hyperbolic equation is a wave equation. So that here we consider the wave equation, the one-dimensional wave equation defined by the equation that I put in a box now. Partial square u partial t square is equal to c square partial square u divided by partial x square, that is defined from x to L for all t greater than 0. And then we have a boundary condition at the left end here, x equal to 0. And we also have boundary condition at the right end when x equal to L here, also equal to 0. And for the wave equation, we have two initial conditions. The first one is the initial one when t equal to 0. We have any kind of function f in terms of x. And the second initial condition, again, of course, it must be at t equal to 0. And we have partial u partial t is equal to another function in terms of x, where we represent it as gx here in general. And our aim is to find the displacement distribution, which is u. And if we draw our wave equation or our domain, this will be look like at the left end and also at the right end we have a boundary condition. So we have here everything here on the left here is the left end boundary condition, while at the right here at x equal to L is our right end boundary condition. So that the value of u at all these x equal to L and also at the left end when x equal to 0, our displacement distribution u equal to 0 no matter what time for all t. And we also have a initial condition at down here, because this one is at t equal to 0 equal to one function. And we also have initial velocity, which is partial u partial t equal to gx. So this is kind of in general our wave equation. And then our focus is on solving this wave equation by using explicit finite difference method. And as you know, our finite difference method is based on the rectangular grid. If you have a domain, and then we put on top of your domain the rectangular finite difference grid, and you can see this is what it looks like, the picture that you can see now. We have our domain from x0 to xn, where our x0 equal to 0 and our xn equal to L based on our general equation that we discussed before. And then for t domain, at the y-axis, we have from t0 equal to 0 to up to tm, where our time differencing for y-axis or for time is k. So here k, maybe we also can say sometime it is delta t. And the space differencing at the x direction, it is h here. And sometime you also can take a look at some books where we use delta x, meaning that it is a space in x direction. And our aim to solve this wave equation by using explicit scheme. And we want to approximate u at arbitrary grid point xi tj. So that at xi tj, so for this one, at xi tj, our u become u sub ij, or you also can write as u xi tj. Okay, this is what we want to find. And if you see in our wave equation, we have partial square u, partial t square on the left hand side. So for this wave equation, we will approximate your partial square u, partial t square with centered difference. Okay, please bear in mind we will use centered difference. So this is what you will get: uij minus 1 minus 2 uij plus uij plus 1 divided by k square. While on the right hand side, what you will have is partial square u, partial x square, and this right hand side we also will approximate with centered difference, but it is for the x, so meaning that we have u I minus 1j, we fix j, and then we have minus 2 ui j and plus ui plus 1 j. While for the t derivative, we keep I fixed and we take the j here. There's a difference between partial square u, partial t square, and also partial square u, partial x square. And then our wave equation now becomes this equation, what you can see now, what I put in a red box. So on the left hand side, you have the approximation for partial square u, partial t square is equal to c square, and then multiply by partial square u, partial x square, where you approximate that second order partial derivative with centered difference. And if you multiply by k square both sides and you simplify, what you will get is ui j plus 1, which is our our displacement distribution at the next level, which is depend on a constant k square c square divided by h square, multiply by ui minus 1j, and then plus a constant 2 minus 2k square c square h square uij plus k square c square h square ui plus 1j minus uij minus 1. Or sometime you also can write this k square c square over h square as r, so that if you use r, what you will get is ui j plus 1 is equal to r ui minus 1j plus 2 minus 2r uij plus r ui plus 1j minus ui j minus 1, where your r is equal to k square c square divided by h square. So this is finite difference equation for our wave equation. And then we also, when we have this finite difference equation, we can take a look at the computational molecules. And if we draw a little bit our computational molecules for this wave equation, so we have for the I level, for the T level, we have, let's say this one at T equal to 0, and then the next level at T equal to T0, T1, sorry, and then for the vertical one we have I in the middle here, and then on the right we have I plus 1, and on the left we have I minus 1. So our computational, what we want to find is U I j plus 1. So let's take T1 as our j plus 1 and our T0 as j. So we want to find at this point, at this grid point, ui j plus 1, and what we must have is u, a constant, multiplied by ui minus 1j, which is this one, what I put red circle, and then minus 2 plus 2 minus 2r uij, this one in the middle, uij, and then plus r ui plus 1 j. And we also have at the previous level for j, where we can write, let's say this one, it is a level of j minus 1. We also need kind of grid that we need here. So this is the thing that we need. And if you see now, if you draw this one, or if you go back to the diagram that you put your wave into, or into the finite difference grid, you can see that at this point, so maybe I can put in a blue one. The blue one here, it is outside of our domain. But never mind, if it is outside of our domain, if you can see our wave equation, the initial involved with derivative, so that we can use our knowledge in first derivative to find what is the value of that blue grid point, which is outside of our domain. So what we need to do is we can discretize our initial condition. So this is the original initial condition. Partial u, partial t at x0 is equal to any kind of function, and then we can write like this one, so that you will get partial u, partial t at I0, so that from we will use a centered difference formula for first derivative also, and because this is with respect to t, so that's why we have j plus 1 minus j minus 1, and this is centered difference. Okay, so you must be careful when you choose your formula. And what you will get is, because we know our j is 0, j 0 plus 1, you will get I, and minus ui minus 1 divided by 2k, because our derivative with respect to t, so that's why we will use 2k. K here stand for time differencing. Okay, that is the overall step, how we solve the wave equation by using finite difference method.